So now we see cross spectral densities, CSDs. That x of t and y of t are the two random processes, and if you let one sample function of x of t is x of t and the sample function of y of t is y of t. So again here we do the same process that we already done in the previous class. Let this xt of t is equivalent to x of t over minus t2 plus t 0 otherwise. Similarly, let yt of t is equivalent to y of t, so over minus t to t 0 otherwise. And also assume both the functions are absolutely integrable for the interval minus t to t. And this condition is also satisfied. So then this xt of omega can be written as the Fourier transform of xt of t that exists because we are letting xt of t is absolutely integrable in the interval minus t to t, and let yt of omega is equivalent to the Fourier transform of yt of t, and this can be written as the Fourier transform of x of t, is it, over the interval minus t to t. Similarly, this can be written as the Fourier transform of y of t over the interval minus t to plus t, because we are letting the x t of t and yt of t both are equivalent to x of t and y of t in the interval minus t to t. Then this particular quantity xt of omega multiplied with yt star of omega. So if you assume both x of t and y of t are real, this yt star of omega is equivalent to yt of minus omega. Let Fourier transform of x of t is x of omega. The Fourier transform of x star of t will be equivalent to x star of minus omega. Is it right? The Fourier transform of x of t is x of omega, then the Fourier transform of x star of t is x star of minus omega. If x of t is real, x of t is real, this x of omega is equivalent to x star of minus omega. Why? Because if x of t is real, x of t is equivalent to x star of t, then x of omega equivalent to x star of minus omega. That is the conjugate symmetry property of the Fourier transform. Is it? So we already know that xt of omega whole square divided by 2t. The expectation of this is the limit t tends to infinity. What is this? This quantity is the power spectral density. Call this as this. Is it right? Now can I write this as limit t tends to infinity expectation of xt of omega into x power of omega. Is it right? Because mod a whole square can be written as a into a star. Is it? That's what I had written. And this can also be written as limit t tends to infinity expectation of xt of omega into xt of minus omega by 2t. Is it right? Why? Because if you let this xt of t is real, then xt star of omega will become xt of minus omega. That is the conjugate symmetry property of the Fourier transform. Now, here we have two functions xt of omega, yt of omega. What will be the xy of omega? Can you write this? This can be written as limit t tends to infinity expectation of xt of omega into yt of minus omega. Understood this? Divided by 2. So this is the cross power spectral density of the random process x of t and y of t. And similarly, can we write sy x of omega? See, in the case of correlation, autocorrelation, we have only one function. In the case of cross correlation, we have two cross correlation. Here also, the cross spectral densities are two, sxy, syx, which is equivalent to limit. So we already know this. So with this knowledge, we are defining the cross spectral density of the two random process x of t and y of t is defined as this. And another density is t infinity, and this is expectation of yt of omega xt of minus omega divided by so these two functions sxy of omega and syx of omega are called as cross spectral densities of the two random process x of t and y of t. Here we are assuming small xt of t, small yt of t are the two functions that are obtained by truncating the sample function x of t and y of t over the interval minus t to t. See, we have the sample function x of t that is truncated to minus t to t. We have sample function y of t of the capital Y of t that is truncated to minus t to plus t. And then we are letting the two functions are absolutely integrable over the interval minus t to t. Then the Fourier transform of those two functions exists. The Fourier transform of xt of t is xt of omega. The Fourier transform of yt of t is yt of omega. Then the cross power spectral density of the two processes are given by those two equations. and we already know that Rxx of tau and the power spectral density are forming the Fourier transform pair. In the same manner, Rxy of tau and this are also forming the transform pair. That is, the Fourier transform of cross correlation function Rxy of tau is equivalent to cross power spectral density Sxy of omega. Similarly, Ryx of tau, Fourier transform of this is Syx of omega. Follow this? So this we already proved. In the same manner, we can write the Fourier transform of Rxy of tau is equivalent to this much. The Fourier transform of Ryx of tau is this. Otherwise, this is equivalent to Fourier transform of Rxy of tau, which is equivalent to minus infinity to plus infinity Rxy of tau e power minus j omega tau d tau. Similarly, Yx of omega is equivalent to, so Fourier transform of Yx of tau is equivalent to, so minus infinity to plus infinity or Yx of tau e power minus j omega tau. Is it clear? Similarly, you can write this Rxy of tau is equivalent to 1 by 2 pi, so minus infinity to plus infinity this is the inverse Fourier transform of this quantity. This is the Fourier transform of this. Similarly, Ryx. We write this. Yes. Yeah, d omega. That is right. If you have two random processes, we can define the cross correlation functions. The transform of these correlation functions, cross correlation becomes the cross spectral densities. So these relations are very, very important, especially in the analysis of linear time invariant systems to the random inputs. If you let x of t is a random process, y of t is a random process. Here, when you excite the linear time invariant system by a random process x of t, the output is also a random process. To analyze the linear time invariant system with random inputs and random output in the frequency domain, we use these quantities, the autocorrelation and cross correlation functions, power spectral densities and cross power spectral densities. So we have the ESD and the ACM. We have the cross correlation functions and the cross density functions. Cross correlation functions. For each cross correlation function, we have the corresponding density function. So now we take up sum of two random processes. Let x of t and y of t are two real random processes. Then we can define a new random process z of t is equivalent to x of t plus y of t. So here we try to evaluate the autocorrelation of the random process z of t. So here this RZZ of tau can be written as expectation of z of t and z of t plus 1. So this is equivalent to x of t plus y of t multiplied with x of t plus tau plus y of t plus tau. So which can be written as x of t plus tau plus expectation of y of t, so y of t plus tau plus two more terms we have. The expectation of x of t, y of t plus tau, and another term is expectation of y of t, so x of t plus tau. So what is the first term? Second term, third term is rxy, and this is the ryx. So therefore this rzz of tau is written in terms of the autocorrelation function of x of t, autocorrelation function of y of t, and the two cross correlation functions rxy, ryx. Now take the Fourier transformation on both sides and see what you will get. So if you let this szz of omega is equivalent to the Fourier transform of rzz of tau, which is equivalent to power spectral density of x of t, power spectral density of y of t, and the remaining two terms. That is, here the Fourier transform of this term rxy of tau. See, rxy of tau is the cross correlation function. The Fourier transform of cross correlation function is denoted as, this is the cross spectral density. Similarly, the Fourier transform of ryx of tau is denoted as ryx of omega. These two functions, see, we already know that rxy and ryx are called as the cross correlation functions. In the same manner, sxy and syx are called as cross spectral densities, or cross PSTs. Cross spectral densities or cross power spectral densities. Therefore, this is, and this is syx